Have you ever flipped a switch and just wondered, how does that light turn on instantly? Well, today we are going on an epic journey to find out. We are pulling back the curtain on the electrical grid, which is honestly one of the most complex, most critical machines humans have ever built. I mean, really think about it for a second. The power plant making that electricity could be hundreds of miles away from you. And yet, the moment you need it, bam, it's there. It feels like magic, right? But it's not. It is an absolutely incredible feat of engineering. So how does it actually work? Let's trace the journey from the initial spark all the way to your switch. The great thing is, we can break this whole massive system down into a really simple three-part story. First, we'll see where electricity is made. Then we'll follow it on its long journey across the country. And finally, we'll see where it all ends up. That's it. Making it, moving it, and using it. So, our journey has to begin at the source, right? The power plant. This is step one. This is where the raw energy that powers our entire world is actually born. The official term for this, the lingo, is generation. And it's exactly what it sounds like, the creation of electric power. And the hero of this first chapter, the machine that does all the work, is called a generator. Now here's the fascinating part. A generator doesn't just create electricity out of thin air. It actually converts motion into electricity. So just picture spinning a giant magnet, that's the rotor, inside a massive coil of wire, that's the stator. That spinning motion creates a powerful magnetic field, and that field gets the electrons in the wire moving. That little push is what we call voltage. Okay, so we've made the power. But a power plant sitting out in the middle of nowhere isn't really useful to anybody. We have to get that energy to our cities, to our homes. And that's where the next part of our journey begins, what I like to call the electricity superhighway. You know exactly what I'm talking about. These are those massive power lines you see stretching for miles and miles across the landscape. You can think of them as the arteries of the grid, or maybe the interstate highway system for electrons, carrying huge amounts of power over incredibly long distances. But here's the thing, a wire isn't just a simple pipe for electricity. It has its own physics going on. First, you've got resistance, which is kind of like electrical friction. It makes the wire heat up and lose a little bit of energy along the way. Then there's inductance, which is a magnetic field that builds up around the wire, sort of like electrical inertia. And finally, you have capacitance, an electric field that forms between the wires, especially when they get close together. So engineers, they have to be master jugglers, constantly balancing these three things to move power efficiently. And this is a perfect example of how that works in the real world. You see, overhead lines, they use plain old air to separate the conductors. But in an underground cable, the wires are all packed super tightly together with insulation. And that closeness, it dramatically increases the capacitance, which actually makes it a huge challenge to move power underground over really long distances. All right, so if the transmission lines are the highways, then what are the interchanges and the exit ramps? Well, those are the substations. You've definitely seen these before, those fenced-in areas that are just full of all this complex-looking equipment. They are essentially the traffic control centers of the entire grid. At its core, a substation is a control point. It's where power coming from all these different lines is gathered together, it's where it gets switched to go in different directions, and most importantly, it's where the voltage gets changed. And if you were to look inside, you'd find a few key parts. There's a bus bar, which acts like a big central intersection connecting all the different circuits. Then you've got switchgear, which is just a general term for all the devices that open and close those circuits. And then you have these massive circuit breakers, which are basically giant safety switches that can instantly cut the power if anything goes wrong. But you know, the real star of the show at a substation is the transformer. Its job is to step the voltage up or step it down. See, to send power efficiently over those long distances, you need super high voltage. But to actually use it in your house, you need very low voltage. The transformer is what makes all of this possible. And how it works? Well, it feels like magic. Magnetic magic. Here's the trick. An alternating current flows into a first coil of wire, and that creates this changing magnetic field inside an iron core. That magnetic field then induces a brand new current in a second coil of wire. And here's the crazy part. The two coils never even touch. Just by changing how many times the wire is wrapped in each coil, you can change the voltage. It's just an incredible way to transfer power right through the air. It's like a gearbox for electricity. Okay, so we've made the power, we've moved it hundreds of miles, now we've finally arrived at the last stop on our journey, Your town, your home, your screen. This is the destination. In power systems engineering, anything that consumes electricity is called a load. It could be a giant factory, the lights in an office building, or even the very device you're watching this on right now. You are the load. So, what do you think uses the most power? The answer might actually surprise you. Looking at this chart, it is definitely not our lights or our TVs. Over half, more than half, of all electricity is consumed by something called induction motors. These are the hidden engines inside pretty much everything that spins or pumps, from your air conditioner and refrigerator at home to the massive fans and pumps that run our factories. They are the true unseen workhorses of the modern world. So we've seen all the individual pieces, right? The generator, the lines, the transformers, the loads. Now let's do what the engineers do. Let's zoom out and see how they look at the entire system, all at once. And here's where it all clicks together. It's not just a collection of different parts. To an engineer, it is one single, massive, interconnected machine. Everything affects everything else, instantly. And to manage that incredible complexity, they have to model it as one giant circuit. And to do that, they translate each of these real-world components into a simplified mathematical model. So, for example, a 100-mile transmission line with all of its complicated physics, it can be represented by a simple circuit diagram. A common one is called a pi model, which is really just a clever way to account for that resistance, inductance, and capacitance we were talking about earlier. And when you put all those symbols together, our entire journey can be drawn on a single page. The generator just becomes a simple voltage source. The transmission line becomes its pi model. The transformer is represented by its impedance and its voltage ratio. And the load, your home, is represented as a component that consumes power. So the ultimate takeaway here is this. It is all one system. That huge generator spinning hundreds of miles away is directly and instantaneously connected to the lamp sitting on your desk. They are all part of the exact same electrical heartbeat. And that, of course, leaves us with one final, very important question. If it really is all one giant, interconnected machine, what happens when a single, tiny part of it fails? Something to think about. Thanks for joining me on this journey.